Assalamualaikum warahmatullahi wabarakatuh. Today we will present about analyzing NiSi-SiC via X-ray diffraction pattern. So what is NiSi-SiC? NiSi-SiC usually refers to a material system in which nickel monosilicide and silicon carbide are combined either as distinct phases in a composite coating as a core shell nanowire, which is NiSi is a core and SiC is a shell. Tools that we use to analyze the data is Origin Pro and Materials Project. Here is a quick side-by-side of the two lattices. NiSi at the top crystallizes in an orthorhombic cell, three unequal axes all right angles. There are 8 atoms per cell unit, 4 nickel and 4 silicon, giving an atomic packing factor of about 56%. So the atoms fill just over half the available space. The interplanar spacing follow the standard orthorhombic formula, and the 3D model on the right shows a fairly dense isotropic network, perfect for use as a low-resistance contact layer in microelectronics. SiC below adopts the hexagonal 4H polytype, two equal basal axes, one longer vertical axis. It also contains 8 atoms per cell, but because the bonds are strongly directional, the atomic packing factor drops to 34%. The hexagonal spacing formula appears under the lattice column, and the stick-like model reflects the open tetrahedral bonding that gives SiC both its wide band gap and excellent thermal conductivity.
Next, for the graph, as shown here, this is the graph of Si and IC that we generated from Origin Pro based on data that given. As we know that this material is combined compound, which are from nickel monosilicide, NiSi, and silicon carbide, SiC. So we compare with those two compound of X-ray diffraction graph for materials project, which is an Si2, Ni3, and SiC. Then we found a significant peak and intensity in both three graphs. As we can look first for Si and I, we got peak from Metro Project is around 40 to 50. And our graph that generated is shown in the same area. Then in SiC graph, even in our generated graph, not shown significant peak, but maybe because of its core shell and combined compound, so it has smaller peak. But still we can see some sparking in the graph, and it has significant area that's shown in SiC graph from Material Project. Next, from the graph that we justify just now, that we find the peak for SINI and SiC, we can work on lattice constant. For working on searching lattice constant, which is a significant thing in a compound structure, we must find some peaks, 2 theta, and its plane orientation. So as we zoom in the graph that generated in Origin Pro, so these are 3 peak and 2 theta that we gain from SINI, that we can see the spark is really significant. And then for SiC, we search for SiC 2 theta peak. So we obtain these two peak at least for working in calculation and insert it in the formula. Next, as we get the 2 theta value, we must find the plane and orientation based on the peak. So we compare it with the Meteor Project's graph for its plane orientation, which is HKL or HKIN. So after working on the math and calculation, we get the lattice parameters, which is A, B, and C, and we get, as a result, we get nearly value with the lattice constant parameters in the material projects that provided. Next, we look to the property of these materials, NiSi-SiC, for chemical bonding, phonons, and electron behavior. For the bonding, NiSi is a metallic and SiC is a strong covalence. So their interface in this material, this is a metal semiconductor junction where NiSi act like a metal and SiC as the semiconductor materials. Next, the phonons. We know that phonons are quantized lattice vibrations and play a key role in thermal conductivity. So with SiC, its strong covalent bonds allows high phonon velocity, which is making it excellent for high temperature applications. For NiSi, we know that it is a metallic bonding, allows electron-phonon interactions. So the metallic bonding allows electron-phonon interactions. Next, we look at electron behavior and band structure. NiSi acts like a metal, so where electrons move freely. This gives it high electrical conductivity, and we can know that there is no band gap each other. NiSiC is a semiconductor with a wide band gap, so electrons are not free unless extra energy is provided. So, based on an NiSi-SiC interface, we know that a Schottky barrier forms, which is this bends the band and affects how electrons move across.
As shown, these are the graphs that we obtained from materials project from both compound. As we can look that these are a wide band gap for SiC compared to NiSi graph. We can look the electron can move freely in NiSi compared to the SiC. That's all from us. Thank you.